To note, we have Dr. Conati, a professor from computer science in University of British Columbia, Vancouver. Professor Conati has done MS in computer science from Milan, MS and PhD from intelligent systems from Pittsburgh University. She has been working in this field, that is AI-driven or human supporting personalization using AI for the last 25 years. She has won several awards by the contribution of this, as the 10 Best Paper Awards, and she has been editor of several top journals, including AAI member, an ACM member, and I've known Professor Conati for last, I don't know, like maybe 10, 12 years. When I was doing my research thesis, I referred her work, I started building my work on it. Then I asked her, we created something on it. I asked her, can you be my reviewer for my thesis? And she agreed. And that's how we started communicating. And thanks, Professor Conati, being here today. And yes.
Thank you. Thank you to you for inviting me, to the organizers. It's exciting. Sorry that I could only arrive last night because of teaching commitments at my university, but better short than nothing, I guess. So I am a professor of computer science at the University of British Columbia. And since some people were asking about it, I figured I would put a little picture there in case I want to, to entice you to come and visit. So that's the campus, and there's the sea, mountains, and Vancouver, it's in Canada, but there are about 33 kilometers of beaches. So people don't know, but it's a beach town in Canada, so quite unique. My research is at the intersection of artificial intelligence, human-computer interaction, and cognitive science, with the general purpose of supporting human-AI collaboration, and doing that with a specific lens, meaning by understanding how to devise AI system that while they interact with their users, they can understand specific user properties such as goals, needs, preferences, personalize the interaction accordingly to these user properties, and also doing that in a way that maintains transparency, user control, and all the other good principles of human-computer interaction. In order to provide this personalization, what we do, we need to set up what is called the personalization loop, where essentially, as the user interacts with the system, the AI mechanisms look at what the user is doing with the system, interface actions, facial expressions, possibly eye tracking, whatever information is available, and the system infers properties that could be relevant to personalize the interaction. And people in this field have worked on tracking a variety of user properties, including, for instance, user goals during the interaction, performance measure, knowledge and knowledge evolution, similar to what John mentioned earlier, cognitive abilities, but also things such as emotions, internal states, and so on and so forth. And there are dots there because this is just a non-exhaustive list. Then once the system knows what's happening with the student or user head, and possibly even emotions, then the question is what to do with this information to personalize the interaction. So there is where the AI comes into play again to make decisions that are suitable. And personalizing the interaction can take a variety of forms, including the system provides help to the user on the task that the user is trying to accomplish, personalize how the information is presented, adapt the interface itself to make it easier for the user to use it, provide recommendations, and so on and so forth. Again, dots there, because these are just some examples. The key point, as I was saying earlier, we want to maintain the interaction between the human and the AI to be usable and acceptable to the user. So the important thing is to deliver personalization in a way that follows good principle of human-computer interaction to ensure usability and user acceptance. So in the space of AI-driven personalization, I've done work on a variety of applications, and including intelligent learning environments, definitely more related to the topic of this conference. I've also done work on using this concept of AI-driven personalization to help users deal with complex and work with complex interfaces. And also I've done work on using AI-driven personalization to help users process complex information. But today I will focus on the work that we've been doing in my lab on using AI-driven personalization to help students learn from educational software. So to build what we call intelligent learning environments. So here, essentially the personalization loop that I showed earlier, instantiated to this particular field of supporting students' learning, just requires for be able to track relevant behaviors that students have as they interact with educational software or other educational tools. Then we need to track and capture relevant user states and properties and use the information. The AI or the intelligent tutor can use the information to provide personalized instruction, very much like a human tutor might be doing in a similar situation. So there has been a lot of work in providing AI-driven support and specifically to problem solving. And as John mentioned in the previous talk, this work has been going on for decades, way before LLMs and Gen AI came into the picture. Sometimes this previous work has been ignored, but there's a lot of it. There's great work. John talks about some very important existing literature from their lab, but there is a lot of other good work that has been done. There is a lot of that, a lot of applications to providing support during problem-solving activities. You know, in all sorts of domains, physics, just naming a few, geometry, computer science, algebra, statistics, and so on and so forth. One specific feature of engaging with problem-solving activities is that often there are well-defined solutions that can be defined and specified a priori, and that we can try to give to the AI as a representation of what the learners should do. And so these existing solutions or components of solutions can be helpful for the AI to understand how to provide step-by-step guidance to students as they engage with problem solving. And often there is a clear definition of correct or incorrect steps that can also be leveraged by the AI to provide feedback. So this doesn't mean that providing AI-driven support for problem solving is easy, but it's a little bit helped by these factors here. But of course, there are other activities that you can do with educational software other than problem solving. And for instance, working through exploration of a domain, working by playing educational games, working with activities that are designed to foster metacognitive learning skills as opposed to specific, the skills specific to the domain. And this is the idea of creating tools that are open learning environments that really try to foster these activities and support students as they engage in these activities that are more exploratory in nature. They're not as structured and well-defined as problem-solving activities. So I'm just going to give you an example of what I mean by this open-ended environment. And the example that I'll show, it's part of a suite of interactive simulations that we developed in the Department of Computer Science at my university. These are interactive simulations that are designed to help students taking AI courses to understand different types of AI algorithms. It's called AI Space, and in fact, anybody, you can access this, is open source. You can try out and even try to use it in your course if you're teaching AI. But there is one of these interactive simulations, applet, is called Constraint Satisfaction Problem applet, and it helps the students understand the working of a specific algorithm for constraint satisfaction. I'm going to show you a little video. You don't need to understand the actual working of the algorithm. You just need to see how the interaction flows.
Provide several mechanisms for the interactive execution of the arc consistency 3 or AC3 algorithm on a set of available constraint satisfaction problems. The mechanisms are accessible through the toolbar or through the direct manipulation of graph elements. Users can perform 7 different actions. The Find Step button can be used to see how AC3 goes through its 3 basic steps: selecting an arc, testing it for consistency, and removing domain values to make the arc consistent. Users can directly click on an arc to apply all these steps at once, or automatically find step on all arcs one by one by using the Auto Arc Consistency action. If desired, the Stop button will pause Auto Arc Consistency.
So this is just to give you a sense that the important thing that you need to get from this video is the fact that the student is not solving the problem. The interactive simulation does. But the simulation provides affordances to the student to decide how the interactive simulation runs and how the student can follow along. So it's really like exploring how the problem is solved by the interactive simulation. So there really isn't a predefined way in which the student should go about using the simulation and exploring the underlying workings of this AC3 algorithm. The idea is that students should work with the simulation the way it's useful for them. And that's a great concept, which can work really well with some students because it really gives them hands-on experience and essentially leadership in how they go about learning the topic. But not all students learn well from these unstructured exploratory activities. So there's a lot of literature showing that. And so it's important to provide supports to the students can get a little lost when the activities are too unstructured. But providing the support in a way that does not interfere with the open-ended, student-led nature of the interaction. So we want to provide help, but still maintain student initiative and engagement. But the challenges here, compared to what we're talking about for problem solving, is that a priori, there is no definition of correct behavior and effective behaviors. It very much depends on the student and how they work with the simulation. So what behaviors should be leveraged by the AI to decide to provide support, and how to provide this support, what signals should the AI use to decide that support is needed, and how should this support provided in a way that is useful but non-intrusive. So these are the key questions that we have been working on in our lab for several years at this point. And we came up with this framework. It's called FUMA, Framework for User Modeling and Adaptation, which is specifically designed to build user models and generate adaptive support from data. So essentially what FUMA does, given data of students working with a specific learning environments, learns from this data what are user behaviors that are an indication that students need help, and then recognizes these behaviors and reacts to these behaviors as new students interact with the system. So essentially, going back to our personalization loop, FUMA is the AI that we use to infer from student actions what are the interaction behaviors that call for help and support. And then FUMA also has mechanisms that, given the identification of these behaviors, decides how to provide help to the student during interaction. So we're going to some details. This is all very abstract, but I just want to say that this framework is general. We have evaluated it with a variety of different open learning environments, including 2 interactive simulations, 4 different MOOCs, and an environment for game design. But in the interest of time, what I will do for the rest of the talk, I will give a bit of a general introduction of FUMA, just to give you a sense of how it works without going into a lot of technical details. And then I will talk about results that we had applying and using FUMA to provide, generate personalized support in 2 kinds of environment, the applet that I showed you in the video, and another environment that is a game programming environment that has been designed to help students grade 3 to 6 acquire computational thinking skills. So starting with an overview of FUMA. So FUMA, the framework works in 2 different stages. So there is a stage that is called behavior discovery, that is essentially the data-driven, data mining part, where FUMA gets an existing data set of data of students interacting with a specific environment, and that can include either action logs, usually that's a given, but could be other data, and we'll see a little bit about that if there is time. It takes these action logs and other data, makes vectors out of it, so representation that allows for every student to be represented in terms of what actions they perform with the interface, and then there is a mechanism that does clustering, which is just a data mining technique that groups students together if they show similar behaviors while they're interacting with the system. And then from these clusters, there are other techniques called association rule mining techniques that, given a cluster of students that seem to be working similarly with the environment, extracts behavioral regularities that represent the specific interaction patterns that cause the student to be clustered together. And so once one has the clusters, one thing that it's possible to do is try to analyze the clusters to see if they belong or they generate different levels of learning with the system. And then once the clusters and the behaviors have been identified from these existing data sets, we create from these structures a classifier that when a new student starts working with the system, the interaction, the actions that the student generates are tracked in real time, and after every action, the student is matched against the clusters that were discovered in their behavior discovery phase to see if at any given point the student shows to be similar to students who have been working well with the environment or not. If the student is matched to a cluster that showed lower learning levels, then the system can say, okay, at this point, the student needs help, and because each cluster has a list of rules that dictate why that cluster represents low learning, if the student shows some of these rules, then the system generates hints related to that. And I'm going to go into an example. This is the general mechanism. So I'm going to show an example of how FUMA works in the context of that interactive simulation that I showed earlier. And so here, if you remember, so essentially there are 7 different actions that students can choose to do when they work with the interactive simulation. Here we had data from 64 students working with the system. They generated about 13,000 actions and about 17 hours of work. So there are 7 different actions they can perform, and for every action, we look at things such as action frequency, so how long each student, how often the student worked with that action or used that action, and also time in between actions, because time is an indication of whether students, a proxy of an indication if students are thinking about what they're doing or they're just clicking away without really paying a lot of attention. So we use time between actions as one of the features that we capture in the rules that we derive from the data. And in this data set, when we apply this clustering technique to look at students who worked in the system in similar ways, we identified 2 clusters, and we had data about students learning. I won't go into the details of how, but we had data of why, if they improved or not when they were working with the simulation. And we found that these 2 clusters corresponded to a group of students working and learning well with the simulation, and a group of students working a little bit less efficiently and effectively. And some of the rules that the system discovered include things such as students who learned well, members of this high learning group, HL. For instance, one action that identified this group is this action of direct clicking on the graph. This just means that the student is very proactive in using the simulation and telling the simulation what it should do. So it shows engagement. This is sort of like an interpretation of why this action is related to high learning. Students that were associated with lower learning, LL, showed not to be using this action frequently, so they were more passive. And also when they used it, for instance, they used it very quickly. They didn't pause after each action to think about the outcome. So there is little time between direct actions when they are executed. So these are just examples of 2 of the rules. There are many others. And from these rules, we derive what are possible actions or suggestions that the system should generate to help the students avoid the behaviors that are not good for learning. So in this particular data set, I don't expect you to read the content of the table. It just shows you that we discovered 10 different behaviors that required help from the system because they're associated with learning not so well with the simulation. And the first 2 at the top are associated. These are suggestions and hints that are derived based on the 2 rules that I just showed you. The first one says use indirect or click more often if the students don't do it. So there's a suggestion that the system generates. And the second one, it's a suggestion that the system generates to spend more time after performing these direct click actions to think about it. These are just 2 examples. One thing that it's important when you have this AI to go in your educational technology is to evaluate if the AI, and in particular the student modeling that you're using, are accurate. Because if the model is not accurate and the system makes predictions that are all over the place, of course there cannot be any useful personalization that the system can perform. So this graph here shows, just to give you a sense, we evaluated how good is FUMA at predicting during the interaction that the student is not learning well, okay? So we ran some evaluation of this part of the model. And what does it show here? So the x-axis shows the percentage of actions that are fed, the student that is being helped has generated. And the y-axis shows the accuracy of the model, of whether the model at any given point is generating correct predictions of whether the student is low learning or high learning. And we can do that because we're doing this on a data set on which we have the ground truth of whether the student is high learning or low learning. And what you can see here is that after seeing about 20% of the actions of a whole interaction with the system, the model already achieves, you look at the black line, achieves an accuracy of about 75% in predicting whether the student is on a good learning trajectory or not, and 20% and 75% in terms of user modeling. It's a good number, although it's not 100%. And after seeing 50% of the action, the model stabilizes in terms of accuracy to be above 80%, and it stays like that towards the end. So this shows that the student model in part, capturing whether the student needs help or not in real time, is suitable. So now what we need to do is to decide what to do with that information. So we have the FUMA classifier that during the interaction at any given point detects whether the student is learning or not, or is predicted to be learning or not, and what are possible suboptimal interaction behaviors that should be corrected or that require help. So now we need to understand what to do with this information and how to actually provide help to the student. And we have two different modules in the environment that do that. One is called the FUMA hint selector, and the other one is a hint presenter. Without going into too much detail, I want to mention, because this is more like the human-computer interaction side of things. So when the classifier, at any given point the student is working, the classifier says, the student seems to be not learning so well, and there are these behaviors, suboptimal behaviors, that are causing the classification. If there is more than one such behavior, we could tell the students about all of them at once. Hey, you're doing this and this and this wrong. Obviously, that doesn't seem to be working. If it's more than one behavior, giving to the student all these hints at once, it's probably going to be confusing and intrusive. So the choice here is that at any given point, we're going to talk to the student only about one problematic behavior. So there is a module that, given all the behaviors that are relevant at any given point and that require help, there is a module that chooses one, the one that is the most salient at the time. I won't go into the detail to tell you how this is done. It's too complicated, but so one problem is selecting which behavior to talk about and to provide hint on. And after that, once you have this behavior, how do you provide a suggestion to the student, a hint that helps the student stop that behavior and engage in more productive interaction? So what I want to mention here, so one thing that we decided to do is because remember, a main point that we want to achieve is we don't want to be intrusive. We want to let the student to be in control when they receive hints and help from the system. And we want the student to still possibly do as much of the work on their own. We don't want the system to tell them what to do. So the way we deliver a hint after we decided that this is a good hint to deliver is in incremental levels of detail. So for instance, if the classifier user model detects that a current student is a low learner because is not using direct or click, Then there is a first level of hint that appears and says, do you know that you can tell the simulation which arc to make consistent next? So here the system is trying to suggest for the student to use this action more. The student can close the hint, is not forced to follow. After seeing the hint and the student continues working with the system continues tracking what the student is doing. If this behavior remains, meaning the student is not following the first hint, then we try to give the hint again. So it's a repeated hint. How to repeat hints? It's, in general, a big problem in sort of like AI-driven instruction. You don't want the user to be annoyed. You don't want the user to be bored. So here we spent a lot of time understanding how to design these repeated hints. For this particular system, we decided to give a rephrasing of the hint itself. You don't need to read it. It's just saying the same thing as before, just pointing out that that suggestion was already given. But also, the system highlights for the student what are relevant arcs that they could click on. So it tries to be more proactive in suggesting what to do next. And one thing that I want to mention is also, I said that these boxes appear on the screen. The students don't have to, they can ignore it, they can close them. But one big question was, how do we make these hints appear so that the student looks at them, sees them, but can dismiss them if they don't want to follow? So I'm just going to show you how they appear in this little video. You can see the hint started from the beginning, and then it moves to the top right corner. The reason to choose movement is because in an initial version of the system, we were making the hints appear at the top left corner right away. But because they would just appear there, many students wouldn't see them. And we know that students are not seeing things because we use eye tracking to check where they're looking to see if they are processing the relevant aspects of the system. So after trying a variety of things to see if we could make sure the students at least see that the hint exists, motion was the thing that turned out the PhD student who worked on this did a variety of user studies, and having the hint appear in one position of the screen and travel to the final position is a way to attract attention to the hint without then forcing the student to see the hint the whole time or the hint to be intrusive. So this is an important aspect of designing this kind of personalization, because the personalization happens in real time during the interaction. So if it's not done well, it can become intrusive. What time is it? Okay, so did this all work? Are these hints useful? So we ran a user study where we have two groups of students, one group working with the applet, the simulation with no support, and another group working with the personalized hint. And there is a paper, the description of the study design. I won't be able to go into the details, but the paper has all of that. So we have the students in the condition with the personalized hints learned more. So we gave them a pre-test, a post-test, and so on and so forth. So this picture shows that the condition with the hints had statistically significantly higher learning gains between pre-test and post-test. And this is a graph showing also what is the, if there is an impact of existing initial knowledge on learning. And as you can see, the systems the students who learned or gained the most when interacting with the personalized hints are the users with the, that had low scores in the pretest. So it looks like the hints are really helping the students who need the help the most. Another point that I want to make here is this, the fact that, so we checked, because you're like, okay, the students received the hints. How do we know that they're actually following the hints? And therefore, the hints are the reason for them to be better when it comes from learning gains. So we checked how often by analyzing the data, their interaction behaviors after receiving the hints. And we noticed that about 63% of the hints that were delivered the first time were followed, whereas 27% were ignored by the students. However, students followed more than 73% of the second level hints, the one that I showed you that repeat the same suggestion in a different way. So this data shows that it is important to sort of be a little bit perseverant as an instructor, in this case an AI instructor, when students don't seem to want to follow the suggestions. After 2 hints, we don't give any more, so we stop after 2, but at least by providing 2 hints, 2 levels of repetitions, we managed to increase uptake of the system suggestion. I want to quickly talk about now of this idea of not just using interface actions to do the modeling of the students, but also use other data. And this other data, we tried with, it's gaze data. So gaze data tracked with eye tracking devices, and we want to see if by putting in our framework information not just on how students work with the interface, but also where they look, can improve accuracy of the model. So we tried this with the ACSP applet. We ran a study with 45 participants, and their gaze was tracked with, it's a T120 eye tracker device that samples gaze data, 120 samples per second. It's something that sits on the, it's attached to the monitor, so it's absolutely non-intrusive. That's the face of a student working with the system when there is an eye tracking going. So the user has no contact with the eye tracker, is not bothered by the eye tracker at all. Just to give you like a very, very little sense of how these eye tracking measures work, what an eye tracker gives you is fixations, essentially points of attention on the screen, which are, and transitions between these fixations. These are standard information that you get from the software. And things that you can use to understand what's happening during the interaction is looking at general measures such as number of fixations that are generated on the screen, fixation rate, how quickly attention moves around, duration of the fixations, like if a person is staring for 5 seconds to one spot, that could have meaning, length of the transitions and some other measures. And these are general measures, and one can also look at these measures based on, in relation to specific aspects on the interface. In this case, areas of interest could be the area where there is the graph, the area where there are the action buttons, anything that could be meaningful. And one can look at these fixations and duration of fixations and all these other measures in each of those areas. So we use these measures as other features that we feed into that cycle of creating the clusters, extracting the rules. And what I'm going to show you here is just that if we have both action data and eye tracking data, sorry, let's see, here is only, okay. So first of all, there is a paper where we show that if you combined these two sources of information, the accuracy of modeling if a student is learning or not gets higher, and these are all like statistically significant results and so on and so forth, than if you use just action or just gaze. So putting together this multimodal information is useful for the AI. And what I'm going to show you here is a graph similar to what I had earlier when we were using only action. But what this graph shows is that the model achieves an accuracy of over almost 90% after seeing only 20% of the actions. Before, if you remember, it was about 75%, and here is 90 already after seeing 20% of the actions. And the sooner the model becomes accurate, the better for personalization, because it means the model can start sooner to provide hints that are justified and solid. So combining action and gaze data improves the accuracy of modeling and the accuracy of the system. I want to say that, however, there is no free lunch. You get an accurate model, but if you remember, from the model, we also want to extract what are the behaviors that are causing a student to be classified as lower learning. And when you look at actions, you see the rules that I showed you earlier that are quite interpretable. The student is not using this action, the student is using this action too much, or using these two actions not so well together. When you start putting eye tracking data, the rules become really strange. So let me see which one I have here. You might have a rule that says the student is classified a low learner because he didn't use this action much, and also the standard deviation of the length of the saccade was too low. What do you do with this information? It's definitely not something that you can tell the student, hey, just reduce the standard deviation of your saccade length. That doesn't make any sense. So in terms of, I think John talked a little bit about this issue of interpretability, right? Now you have a richer model, but what the model gives you to work with when it comes to making having actionable items that we can deliver to the student, then it becomes trickier, because now you have this information that is very low level, very hard to change. So unfortunately, we're still kind of thinking about what to do here, but some of the things that we're thinking about, I don't want to discount the idea of using multimodal signal for student modeling, as multimodality is very important and promising, but there are some caveats. So one option would be to just use the multimodal data just for classification, and then still manage somehow to disentangle the things that are too low level to tell to the student, and see if you can then still have hints at the level of actions that make sense. Use higher level gaze features that are more interpretable in terms of don't look away so much, look at the bottom, those kinds of things. But again, these are all ideas. And in general, there is this trade-off between the accuracy that you get from multimodal user modeling and then what you can do in terms of interpretability. Okay, so I guess I still have a few more minutes that I want to use to talk a little bit about this newer work, in which we applied FUMA to provide help, personalized help to kids working with a game programming environment to foster computational thinking skills. So, so we're down here. So this environment is called Unity CT, Unity from the platform for game development, CT for computational thinking. And so this work is done in collaboration with a company in Vancouver, Yumi Academy, who created using Unity CT an environment, a curriculum that was designed to help students acquire computational thinking skills by building games, following instructions and assignments given by instructors from this Yumi Academy. So essentially, the platform allows, it's a simplified version of Unity because it's to be used by kids. And so students are given challenges or goals for the games that they need to design. And then they have free-form interaction, where they can engage in free-form interaction with the platform to create the games that achieve these challenges or objectives that are given to them. Here are just a couple of examples of things that they can engage with or create. So this company had devised this curriculum to work as extracurricular activity. So they were offering it in person before COVID, during summer breaks or as afternoon, after school activities. The way it worked in the past, it's like you see in that picture. So you see the kids sitting in this room, and they're given the challenge. So every lesson, it's one challenge or game that they have to build. And there is one facilitator and instructor from the company that is there to provide help. So now in this picture, some of the kids are working together. In reality, it's a one-to, so the kids are working on their own. So this is the way it worked before. But then after COVID, the company really thought it was a good idea to try to also have an online version of this platform and this curriculum. So now they have a self-directed. So this thing is online, and kids can access any of the lessons in the curriculum whenever they want. They can work with peers. It can be done by a teacher in the context of a classroom or not. It's completely open-ended how it's done. And so the company came to us to see if we could have, and of course, because now it's self-directed, any help that the instructor was giving during the in-person workshops or sessions is not there anymore. So we wanted to see if we could have AI agents that can provide help in real time as students work with Unity CT remotely on their own or with their peers, we don't know. So essentially what we did, we have several papers that discuss and show how we apply the FUMA cycle that I showed earlier, behavior discovery, building classifiers, to data sets that were collected of students working with Unity CT. So again, we do exactly the same conceptually. So we look at student interaction data with Unity CT, then FUMA derives behaviors that are relevant or detrimental to learning, and then from this behavior generates the rules that justify or explain when these behaviors happen. And then in this case, we also had a lot of work that we did with the people from the UMI Academy, the instructors, to understand how to deliver the hints. Because I already talked earlier about how important it is to design the hints so that they're non-intrusive, but they're still visible. But that was in the context of the CSP applet, which is used by university students who are, in any ways, doing homework for their classes, so they're already in that space. Here, it's more challenging because this is designed for kids who are kind of, having fun. They're really engaged because they're building their own games, right? So getting hints on how they should do it differently can be tricky. To have these hints be accepted and well digested by the students is tricky. So we did a lot of work with the user experience experts from the company and instructors to make sure that the hints are delivered in a way that students decide to use. So for instance, I'm not going to go into a lot of details, because again, in the interest of time, but one thing that I want to mention is this idea of repeating the hints, which we already saw for the previous for the previous environment. So here, for instance, again, the idea of repeating the hints when students don't seem to pay attention, it's still current or relevant. And in this case, we have a whole paper, or two actually, that talk about, so for instance, there is the first hint, hints are given again at different levels of detail. So if a student is showing a behavior, for instance, there is a thing that if you're building a game, then you switch to a mode that is called play mode, where you can test the game that you have so far. If you make changes to the game as you are in play mode, you lose all your changes. You have to get out from play mode. This is an error that happens often. And so it's one of the things that now the agent generates a hint for if the student shows that behavior. So the agent would say something like, oh, look out, your changes will not be saved because you are in play mode. The student can choose to ask for more help, and then the system says exit play mode so that you won't lose your future changes. And this is one first hint that is given. If the student shows this behavior again, what do we want to do? We tried a variety of versions where this sequence was repeated with different wording, but still like it was a sequence, and didn't quite work. And now we have a version when if the hint needs to be repeated, the two levels are combined in one go. So the student sees a repeated hint that says, remember, editing in play mode will cause you to lose your changes. To avoid the problem, exit. So the student says the information all at once. And we have, in these papers, we have a detailed analysis that shows how making that small change made the hints much more effective. And then we have, just to conclude, we have a final evaluation that we conducted in the wild, meaning we deployed a version of Unity CT with the agent that provides hints in real time and a version that has nothing. And this is like done, we have no control on how students use it. We don't know if they're using it by themselves or with peers, nothing. So the paper has all the details of the challenges of doing that. But essentially, and this is just a few of the hints that the system can generate during the interaction. And we have results in this paper showing that if you provide those hints to the students, they are better able to create suitable game solutions, which are, of course, a precursor to learning to do computational thinking. We don't have yet a formal evaluation of the higher level computational thinking skills, because it's really hard to give any test to the students since they are online. We don't know who they are, and they don't want to take questionnaires afterwards. But this is a very, very good result. So I'm going to skip all this in the interest of time. And I'm going to say that to conclude, oops, too fast. Sorry, I'm just going to say my conclusions, and then we'll let everybody go to lunch. Okay. Okay, so I presented a framework for data-driven user modeling and personalization that we have evaluated with several learning environments. I haven't talked about the other ones for the lack of time, but I'm happy to give you the references if you're interested. And we really have evidence that we can identify clusters with behaviors that are supportive of learning versus not. And we can classify students in real time based on these clusters and behaviors. And we can design and drive personalization that has shown to be effective in terms of helping students work better from this open-ended exploratory interaction. And so we have evidence that it works, and we also have evidence that if we explain to the students, I'm not going to go into too much detail on that, but if we explain We add to the system the ability to explain why the hints was generated. That even increases effectiveness. And for future work, we really want to apply FUMA to other environments. So if you have any open-ended environment, an interactive simulation or game, and you're interested in working with us to see what FUMA can do there, we'd love that. Very important to do future experiments with multimodal data, like eye tracking or facial expressions or other things. We want to consider student affect in providing hints. We haven't looked at affective states of the students at all so far, but they are very important. And of course, where do LLMs fit into all this? Well, it's a big question. For sure, we think we could definitely use LLMs to help verbalize the hints in a richer and more varied way, and definitely continue working on the explainability of the hints for the students, because that's a promising action. So thanks these are all the students who worked on this and postdocs. So they are the main force behind this work. And thank you to all of you for your kind attention.
Thanks, Professor Conati, for a wonderful talk. And you walked us through the FUMA from the log data interaction and adding aegis data to provide personalization. And you've shown an impact of that using two systems. It's wonderful. We have no time, but I just have one question I can take. Yeah.
If there is two, maybe. I came all the way from Vancouver last night.
Okay.
16 hours.
So my question was, do you really think that these fixation and saccade changes, to be more specific, decreases while being in a joint collaborative learning settings? Like a student in individual behaves differently while being in a peer group. So is it decreases?
I have a hard time to hear because of this.
Sorry,
the fan is very loud. So it was about eye tracking.
Yes.
And you're saying if the behavior, eye tracking behavior changes.
Yes, I was saying that the saccade and fixation decreases while being in a joint collaborative learner setting. When
if they might change when if you can use that to check for collaborative interactions?
Yes, when students are in a group, then.
Oh yeah, that's a great question. There is a lot of work that started looking at that. A lot of work with eye tracking in collaborative settings has looked at more interaction between, among humans, and if you can capture, say, attention and gaze to people when they talk versus not, and so on and so forth, as opposed to two people collaborating with an environment, because it's much harder to follow, because if you're not looking at the screen, then you cannot use the screen-mounted eye tracker. You need to use glasses. But if you look glasses, which are good for person-to-person interaction, they're not as good for... So there are some technical complications that has prevented this particular question to be explored in detail. It's super important, and I'm confident that eye tracking technology will get there. At this time, it's a bit hard, but I think it would be a very important source of something that should be definitely be looked at.
Thank you.
Yeah.
Okay, so one more question here.
Thanks for your talk, Christina. I think it was a very elegant demonstration of how we can use tracking of behaviors for actually giving students tangible, actual hints. I just wanted to pick up on the last point that you made very briefly, which was about telling students why they're getting the hints that they're getting. And actually, in my AI Ed course, I had that chapter on scrutable AI Ed, that you and Judy K authored actually. So I was just thinking, what are the advantages and disadvantages of this? Because I can imagine some cases where if you give too much information, yes, it probably can increase trust. But do you see some boundary cases where this may not work, and how should we think about scrutability in that sense?
That's a great question. And you're right, I mean, I went through it very quickly. But so actually the concept I just talked about explainability, but in our group, we're actually working on personalized explainable AI, because explanations of why the system is suggesting certain things and so on and so forth, they're not always useful for all users. They're not always wanted. It's very much user dependent, context dependent. There are a variety of factors. So in fact, I said we show the explanations work. In fact, it depends on some user characteristics. So it works for some users and not for others. So one main guiding criterion to use, provide the system with the ability to provide explanations is to make the explanations really to be a choice of the user to ask. And what level of detail, how much explanation, what kind of explanation, it should all be designed so that it's the user that decides what they want. Because it's really difficult to design explanations, one size fits all, that are good for everybody, especially in an educational setting, when they are already in cognitive load to learn the domain, and then they also need to listen to explanations of why the AI is doing something. It's very complicated. So we have some papers that talk about it, but we can follow up.
I think that just also made me think about help seeking, and because that would come into picture as well, right? Do students know? I mean, is this help seeking in some way? It's probably a little bit different from help seeking, right? Help seeking. But it's still seeking information about.
Help seeking.
Yes, help seeking. Helping, oneself to understand why certain recommendations are being made, or why certain system choices are being pushed.
Absolutely, absolutely. And again, it's, in a sense, it should be a way to convince the students that the system is providing good help and should increase the desire for help seeking as opposed to help avoidance. But again, it is not that easy. Okay, so there are complexities that relate also, among other things, to student characteristics. So I have a couple of papers that I can send you if you're interested. But yeah. Okay.
Thank you.
Yeah, thanks everyone. Thanks, Professor Conati. And there is a small memento from the conference organization.
Thank you. Oh, it's beautiful. Okay. Thank you.
So Conati is available during the lunchtime. Plus, if you have any questions, please, I know a lot of you have questions, but please carry on during the lunchtime.
Right. Okay, I didn't go too much over time. Yes.
Sorry, it was like this delays, that's why.
It was an hour.